Welcome to Energy System Modeling Exercise 5. Again, the exercises can be found from the Moodle folder, so you can go ahead and download the whole folder. So let's start with the first assignment in here. And so download the Energy System with Storage Excel file and determine a battery size and charging and discharging rate with which you can cover 90% of the consumption together with the renewable production. So let's go ahead and open the Energy System with Storage. And in here, we can see that we have time. It's in minutes, and in here it's converted to hours. And then we have solar production, wind production, and consumption. So if I'm going to draw these ones in here, it looks something like this. So there's the solar production on the blue, there's the wind production on the orange, and this is the consumption. So we would have to, so from here we can see that, for example, in here, there's excess solar production compared to the consumption. And in here, there's lack of production compared to the consumption. And again, in here, you would have to do curtailment because there's wind and solar, and even the solar amount is going above the consumption. But the renewables don't cover everything in this system, so we're going to have to arrange a battery for it. So let's make a little room in here so I can put the initial values in here. Maybe like this. So I'm going to say battery size. It's going to be 20 kilowatt hours. Or let's put maybe 10 in the beginning. So that's how many kilowatt hours. And let's put a charge rate. It's usually in industrial batteries, it's somewhere between 0.5 to 1. So if this is 10, it's going to be 0.5 or 1 times this one in kilowatts. So this C coefficient would be, let's say, 0.5. I'm going to put a little lower in here for the sake of example. So the charging and discharging rate. So charge rate, this also is the discharge rate. It's going to be 0.3 times this one, and it's going to be in kilo, or not kilowatt hours, but kilowatts. So our charging limit, well, if we first look at the DT, it's going to be 0.25 hours. So let's mark that down in here as well. So DT is going to be 0.25 because if we're inspecting a time step of 0.25 hours, then that means that our charge limit, let's call it that, charge limit in energy is going to be this one times this one. So you can, during 1 hour, you can input 0.75 kilowatt hours to the battery. So at first, let's start looking at this data. And what we can do is we can start calculating the renewable production. So renewable in kilowatts is going to be wind plus solar. So again, if I'm going to see it in here, I can change this one to include the both wind and solar. So after that, what we'll have to do is we'll have to determine what kind of a shortage or surplus do we have. So I can call this surplus in kilowatt hours. So how many kilowatt hours are in surplus? Or rather kilowatts, not kilowatt hours yet. Or actually, we could do that with the energy. I think that would be better. So now we're going to have the calculation steps in here. So let's put steps. And I'm going to start from the second value. And what that means is that when let's put it in the whiteboard. So if I have, for example, an hour worth of value. So this is time, this is hour, and you have 0 in here, 15 minutes, 30 minutes, 45 minutes, and 1 hour, 60 minutes. And we have these data points in here, for example, in here, 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 and here. That's our power readings at that current time. So that would mean that we could get an average out of these. So average for this and this, you could also calculate it in this kind of a trapezoid style. But let's have an average of here. So it's an average of this one and this one. So the average of this and this is going to be here. This is going to be here. And this is going to be here. So you're going to have kind of 4 columns in here. And they are going to represent the energy. So we had 5 values, but we have 4 energy columns. So that means if we are talking about this energy, we're trying to determine what amount of energy has been produced or consumed in this time span. So rather than looking at the time points, we're going to be looking at the time spans. So in here, that's why I'm going to start from this second row. So it's going to be this time span. The next is going to be this one, and so forth. So let's calculate the energy. I'm going to say solar, or the renewable rather. Renewable energy, and that's going to be in kilowatt hours. So let's have an average out of that. Average of this renewable from here. Like that. And then we'll have the consumption in kilowatt hours. And again, we can use this one. I'm going to switch it from here till consumption, like that. And actually, since we're calculating energy, then we're going to have to multiply this one with the time step. So let's dollar that. And for here as well, so times time step. So you can see that it's 4 times less because we only used quarter of an hour. Okay, so now renewable energy is being produced during the first time span. It's going to be produced this amount, and the consumption is going to be this amount. So then we have the surplus. So now, rather than calculating the power surplus, we're going to calculate energy surplus. So surplus is going to be kilowatt hours. So it's going to be consumption, or rather renewable energy minus this one. So that's how much surplus is in there. And you can see that it goes below 0 if we draw it. So in here, we don't have surplus, rather we have demand of additional energy than just the renewable one. But if we're talking about the battery, now we determined that our charge limit is going to be this one. So we can't fit during this 15 minutes. We cannot fit into the battery any more than 0.75 kilowatt hours, or we cannot discharge it any more than 0.75 kilowatt hours. So now I'm going to have an if statement in here. So there's going to be surplus limited. That's going to be kilowatt hours. And we're going to say if this number is going to be below minus 75. So if it's less than the discharge, so minus, then what's going to happen? It's going to be minus this discharge. And otherwise, we're going to put another if statement. So if this one is higher than this value, then you're going to give me this value. And if not, then it's going to be this surplus. So now if I draw this, you can see that it's limited during these hours or these moments where it before had a larger spike than our battery could have handled. So now it's limited. And then we're going to give the battery a boundary condition. So let's put state of charge 0, which is going to be, let's say, 3 kilowatt hours. Or actually, I can put again, let's put half. It's going to be half full, 0.5 times this one. So whenever we change this battery size, then both of these charge rates and the charge limit that's derived from it and also the state of charge are going to change. Let's keep it at 10 now. So in here, we're going to start from this point. So what is the battery state of charge at that point? So we're going to mark it in here. State of charge is going to be this one. And now I'm going to start loading the battery. Or then I'm going to start charging or discharging, rather. So in here you have surplus, so we're going to have to start charging the battery. Or don't have to, but we can. So let's put this one plus this one. But if we just do it like this, if we don't have any kind of a limiter in here, then it could go below 0 or above the charge limit. So I'm going to control X these ones, and I'm going to start making an if statement. If this one, so let's take the parentheses to the copy. So if this one goes below 0, then you're going to give me 0. Otherwise, you're going to check again with another if statement that if this value goes above battery size, which has to be $, then you're going to give me the battery size. Otherwise, you're just going to give me this one. And something seems to have gone wrong in here. Yeah, one more parenthesis than needed, or one we did in here. So let's see if I did it. If I did it right, I can show you it again in here. So there's if statement in here. This is the logical test. Value if true, then value if false. And this is the other statement, or the rather the second statement, or if values. So value if, or rather logical test in here, then value if true, and then value if false. So before we had just this one. But now we're going to have to check if it goes below 0, then it's 0. If it goes above the battery size, then it's just going to be the battery size. So let's see this one. And now I can try and draw these. Actually, I could draw it in a way that there would be, well, let's see the consumption and the battery. That's the battery state of charge. Yeah. So it behaves in a reasonable way. So what we want to do after this one is we want to calculate, let's see, if we have this consumption in here, or rather the renewable energy in here, and we have the battery state of charge. So I'm going to calculate renewable energy plus what's happening in the battery. So this would be, I'm going to call it production. So this is what the consumption time series sees, how the system can provide this consumption to it. So this is going to be again in kilowatt hours. So let's see. I have this amount of renewable energy, and what's happening in my battery, I'm charging it. So that's why I'm saying minus this one minus the previous. So let's see what that looks like. And I have the consumption in here, and then I have the production in here. And now I'm going to draw, insert from the charts, I'm going to draw this kind of a line graph. So from here, you can see that these represent, each of these columns or column pair represents one time span that we are determining. So this one and so forth. So I put side by side the consumption and the production. And as you can see in here, the production doesn't match the consumption. And that is why, or that is because rather, our battery doesn't cover any more of the energy demand that's being left from the renewable energy. So let's see this one again. So renewable energy was like this. So there's the power consumption and power production from the renewable energy. In the beginning, the battery can be charged in here. This figure doesn't show it, by the way. But the battery can be charged. You can see it from the battery state of charge in here. So the battery is being charged. We can actually draw that one as well. So we'll see it like this. So first the battery is charged. Then it stays constant in here. So no, well, that's probably only one time step in here. But then the discharge starts because there's a need for this additional energy. And as you can see, there is something that you have to curtail. So there's too much energy to fit into the battery at this point. So that represents this part in here. Too much energy for the battery, so you cannot do anything with it. In here, it's limited by the maximum amount that you can fit into the battery. So it's this part, I guess. And these spikes represent the limit of the charge. So you cannot fit during 15 minutes more than a certain amount to the battery. So that's the capacity limit and that's the charge limit. And now if we were to calculate how much we can cover from here, then this production, it's this one, I can say that if, let's take this one out of the way. So how to say, well, we can just call it, this would be overall production, and this would be kind of the coverage, kilowatt hours. So we're going to say if this value is going to be above the consumption, then you're going to give me the consumption, because it always kind of maxes out in here. We cannot utilize this one. We have to curtail that. And otherwise, it's going to be this one. So let's draw this one to the chart rather like this. So it cuts out everything from above here. So if production is greater than consumption, then you're going to limit it. And now what we can do is we can calculate, well, the total coverage. So total coverage, that's going to be, let's put it unitless. So I'm going to have a sum of this coverage, and I'm going to divide it with the sum of consumption. And it should be below zero, at least based on the, so consumption in here, at least based on the figure. Yeah, so 87%. And the assignment was that we had to determine a battery size and charging/discharging rate with which you can cover 90% of the consumption together with the renewable production. So let's do that. Our total coverage has to hit 90%. So if we change this one to 20, it's going to go above it. But again, if we don't have initial state of charge, so if our initial state of charge would be 0.1, you can see that if we increase the battery size, well, now it actually does it. So let's put 0 into here. No matter how big of a battery I put in here, it still cannot cover any more than 86%. So that's why I have to have some initial charge in there. That's really important for this system because there is such a long time in here, or rather such a short time in here to start stashing up the energy. So this energy wouldn't cover everything that you need in here. So that's why you have to have something in the battery in the beginning. So let's use this data tab, what if analysis, so goal seek, this has to hit 0.9 by changing the battery size. And the battery size is going to be 11.3 and so forth. Total coverage is 90%, and we gave it some initial values like the C, so how much charging rate is compared to the battery size, kilowatt hours and kilowatts, and we had initial charge of half full with the battery. So there you have the first part of these exercises. And the second one is to acquire the hourly electricity price in Finland for the year 2023. Set a size and discharge power for the ideal storage and use Python to determine the arbitrage profit with price limit for charging, so buying and discharging, or rather charging and discharging, so buying and selling, and this rolling horizon of 24 hours and an optimization algorithm of your choosing. So what we want to essentially do in here is if we have a electricity price that fluctuates like this, we're going to set a price limit in here about which this is going to be, we're going to be selling. So in here, there is price. So this is euros per megawatt hour, and this is time. So this is going to be sold whenever we are above here. This doesn't represent actually the area in here, anything that above the price line. This isn't the energy. So we have to determine a battery size. And if we have something, so at each time step, you're going to have to check what is your battery state of charge here and here and here and so forth. And can you sell or do you have to buy? So buying is when it's cheap, when it's below here, and selling is when it's a high price in here. You could also have two separate lines in between, which wouldn't happen to anything, but let's set one line in here. And I gave you the prompt in here. So this is the prompt for limit-based arbitrage. So you can use this one. And again, you want to be precise. So write a Python script that simulates energy storage arbitrage using a battery and electricity price data from an Excel file. The goal is to track battery charging and discharging based on predefined price thresholds and calculate the total profit over time. The data input is going to be read the Excel file. So in here, you can see that it's price 2023. So I took Finland prices for 2023, assuming the first column contains hourly electricity prices. And battery specifications. Again, this is something that you can choose at random. And for this exercise, I could say that this is a really small number if it was a battery energy storage for power compared to its capacity. So usually this would be rather high in comparison to this one. So it could be, for example, this 20 kilowatts or 10 kilowatts in that range. But we can also utilize some other kind of energy storages, so it doesn't have to be a battery. So that's why I chose something like this. But of course, this in that sense is a bit misleading. So, but either way, capacity and maximum charge and discharge rate. And then you have the arbitrage strategy, buying condition. If the electricity price is below, let's say 20 megawatt hours, and there is space in the battery, buy 1 kilowatt of electricity or kilowatt hours, however you want to prompt it. So at this point, I'm going to say that only use this maximum level of this charge or discharge. Now the selling condition is going to be that if the electricity price is above 20 megawatt hours and the battery has stored energy, sell 1 kilowatt hour of the energy. Buying incurs a cost, which is cost times power, or rather cost equals power times price divided with 1,000, because we had kilowatt hours and this is in megawatt hours, or rather, kilowatt hours and megawatt hours. And in here, you can state to the prompt or the AI rather that this is what it's for. Selling generates revenue using the same conversion. So the script should track battery level over time, profit per hour, and cumulative profit. And after that, you can set for the visualization. So you can store results in list for hourly profit, battery level over time, and cumulative profit. And then you can plot cumulative profit over time, battery state of charge over time, and electricity price over time. So with this, I was able to generate this limit.python. So let's go ahead and open that. And remember, again, if you have to install these libraries, you can do it from here. So you have the file settings. Then you have project, Python interpreter. You press plus and you write, for example, pandas in here. And then you install the package. I have these pre-installed already. So let's go ahead and see what happens if I run the code. So it gives me this kind of window. So there's the cumulative profit, and that's the battery state of charge. So in here, you can zoom in what's happening to the state of charge. When are you, so it starts from 0, by the way. So you can see in here, if our limit was 20, in here it dips, or maybe this one, it dips below, no, it's in here, yeah. In here, it dips below 20. And then you can again sell it when it climbs up. And again, it's dipping below 20 and then rises above 20, so you sell. So there you can see that there's a small decrease in here. So that's when you buy, and this is when you sell. And again, when you buy and when you sell. And what I did also in here is I made a price day Excel file in which I determined that the price was this many hours, 10 euros per megawatt hour, and the rest was 60. So what you can do with that, so let's go ahead and change it in the code. So in here it would be day, and let's see what happens. So now you can see kind of like in a controlled environment, what happens. What happens to the electricity price? It makes this kind of a step change. So in here, you're going to charge, and after that step change, you're going to discharge. You're going to buy, and after that, you're going to sell. So it behaves in a reasonable manner. So that's a good way to kind of test your codes. And the other one was using this rolling horizon of 24 hours and an optimization algorithm of your choosing. So again, I have a ready prompt that you can use, but it's better, of course, to make your own prompts and be specific, precise. So again, we start with this. So the data input, it's rather similar than before. So the data input is going to be the same one. Battery specification is going to be the same one. And now the optimization method. Implement a rolling horizon optimization approach with 24-hour look-ahead window. And in here, it's specified what optimization method has been utilized. So it's going to optimize the loading or rather charging and discharging. So it's going to take 24 hours from here, for example, and then it's going to use these price values to determine an optimal charging and discharging strategy. And it's only going to take the first value from that charging and discharging strategy, and then it's going to move the horizon 1 hour ahead. And again, after that, it's going to move it 1 hour ahead. And it's going to optimize always the entire 24 hours from the beginning to the end, but it's only going to take the first value from the discharging and charging strategy. So the objective function should maximize profit where charging incurs a cost and discharging generates revenue. Ensure that battery state of charge never exceeds its capacity. State of charge never goes below zero. And that was something that we determined also in here with the, let's see, the state of charge for our battery. So it's this one. This is the state of charge. So don't go below zero or don't go above maximum capacity. And charging and discharging power at each time step represents the limit of plus minus 1 kilowatts. And at each iteration, only apply the first decision from the optimized sequence and move forward in time. So that is this is all the storing the results and writing them in an Excel file. That I wanted to do that as well. So battery results. And then on top of that, I think I put a progress bar in there as well. So now if I use this rolling horizon, and it's the price for, it was 2023 in here. So you can see that there is the progress bar. And we can wait up till it completes the optimization. So each time step, it's going to see 24 hours into the future, what are the prices, and that is a rather it's like a possible task for this optimization algorithm that I'm using. But if you were to optimize the entire year, that wouldn't be possible. There's too many variables for this optimization algorithm. So now we got to this cumulative profit of this is what, 95,000 euros. And in here you can see the battery level and charging and discharging power. So this is the strategy. So when to charge and when to discharge. And that is based on the price. So if we use this limit and see this one again, so let's put it for the in here. This is going to take a while. So cumulative profit, it's going to be some 50. And I think it's missing thousands from here. This doesn't make too much sense if the other one went to 90,000. But either way, this limit is less effective as an optimization strategy. In here, you're going to only see the battery state of charge rather than the charging and discharging strategy as well. So those were the exercises this time.